All right, next section is row operations. Now what's going on here? The idea with this section is we're going to continue our translation of equations into matrix vector notation. Now, we've seen back here that we can do things to equations without changing the solution. If we have a list of equations, we can swap two equations in the list of equations. That won't change the solution. Or we can take any one of those equations and multiply it by a certain number. That won't change the solutions. Or we can take two of the equations from the list, multiply one by a constant, and add it to the second. That won't change the solutions for the system of equations. So we have three operations that we can perform on equations, on a system of equations rather, that does not change the set of solutions. All right, so let's translate this idea into our matrix vector notation. We've just seen three equation operations. These correspond to three row operations. All right. Now, before we said we could swap two equations and not change the set of solutions. So our first row operation is swapping two rows. We said that we could multiply any equation by a constant. That is, you'd multiply every coefficient in the equation by the same constant, and that would not change the solution of the equation. So our second row operation corresponds to that. It says if we multiply every entry of a single row by the same quantity, that's our second row operation. The third equation operation we talked about was taking one equation, multiplying by a constant, and adding it to another. As in terms of row operations, that corresponds to this third row operation. Multiply each entry of one row by some quantity and add these values to the entries in the same columns of a second row. That's exactly what we're doing here. So this notation makes it easier to see what's going on. This means I swap row I with row j. Now, of course, when you're doing it in real example, you'll have a specific value for I and a specific value for j. Or I can multiply row I by a constant, or I can multiply row I by a constant alpha and add it to row j. All right, so these three row operations correspond to the equation operations we've talked about before. Now, we've said that if you do these operations to a system of equations, you don't change the set of solutions. So in some sets, the equations that you get are equivalent. We're going to define a notion of equivalence that corresponds to this for matrices. We'll say two matrices A and B are row equivalent if one can be obtained from the other by a sequence of row operations. All right, so let's see how this works in practice. Here I start with one matrix A, and here's another matrix B. To start off, they don't look all that similar. There's some similarity. Well, let's see how similar are they. All right, look here. The last row here is the first row here. The first row here is the last row there. It seems that the rows of A have been swapped to obtain B. Now, this second row of B looks different, but we'll see how we can get that from A. Right? There's actually a sequence of row operations, and here they are. And the first row operation was we took A and we switched the first and third rows. So third row here goes up to the first row. First row here goes down to the third row. Now, taking this matrix, we can take this matrix. This operation says take -2 times the first row plus the second row. So what that means is I take every entry in the first row, multiply it by -2, add it to the corresponding entry in the second row, and replace the second row with the result. You always replace this second row in the row operation with the result. And we'll see what that means in other examples. So how does this work? Let's see. Minus 2r1 plus r2. How does that work? Minus 2 times 1 plus 5 is 3. That's how we got this. Minus 2 times 1 plus 2 is 0. Minus 2 times 0 plus minus 2 is minus 2. Minus 2 times 6 plus 3 is minus 9. So that's how we get this. So we can see that these two matrices are row equivalent. This one was here. This one was here. We have a sequence that relates them, so they're called row equivalent. It turns out that if they're row equivalent one way, you can also go backwards. And we'll see that later. But there's a way to go back from here to here. And going back from here to here is very obvious. We can simply replace row 1 through, we can exchange row 1 and row 3 and get from this matrix back to this matrix. Okay? Now, we've said that if you have two systems of equations and you perform equation operations on them, you get a system of equations that have the same solutions. Now we're talking about row operations, and we can express that same idea in terms of row operations. All right? So suppose that A and B are row equivalent augmented matrices. Then the systems of linear equations that they represent are equivalent systems. And the proof is simply that we're doing the same thing with rows that we did with equations. We're just using a different notation. Okay, let's go back to an example here. Here's an example that we did before. Let's see what it looks like here. Now, look at this very involved way to solve a sequence of equations. You take these equations and then you add minus 1 times equation 1, add it to equation 2. I don't want to go through all of this, but this is a lot of writing. We're going to see how you can do this with much less writing. First of all, we get rid of all the variables and write it as an augmented matrix. You can see on the left-hand side here, you have the coefficients. On the right-hand side, you have the vector of constants. And here we have a system of row operations. Now you can check these one by one and make sure that these actually work. If you take this matrix and you take minus 1 times the first row plus the second row and replace the second row with the result, let's just do a couple of these. If we take minus 1 times 1 plus 1, we get 0. If we take minus 1 times 2 plus 3, we get 1. And you can check the rest of the entries here. If you do this operation, minus 2 times r1 plus r3, and replace the third row with the result, well, we're working off this matrix now. Let's see what happens. Minus 2 times 1 plus 2 gives you 0. Minus 2 times 2 plus 6 gives you 2. So these work out. And you can check the other ones. Now, we didn't ask the question, why did you do these particular sequence of row operations? We'll talk about that later. But just notice the pattern here. This matrix here has a 0 here. This matrix here has a 0 here and a 0 here. This matrix here has a 0 here, a 0 here, and a 0 here. Furthermore, this matrix has a 1 here. This matrix has a 1 here and a 1 here. This matrix has a 1 here and a 1 here. My final matrix here has a 1 here, a 1 here, a 1 here, and then zeros down below. So it has a stair-step pattern of 1s underneath which you have only zeros. Okay? So my final matrix was this matrix here. And the theorem that we have up here calls it REMS, which is this theorem up here. What we talked about here says that this augmented matrix represents a system of equations that has the same solutions as my original system of equations. All right? And I can easily write this back as a system of equations. I just put the variables back in. This first column is x1, second column x2, third column x3. The fourth column is the vector of constants. Okay? Now to solve this is very straightforward. You work your way from bottom to top. Okay? If I have x3 equals 4, then I can write x2 plus, I can plug in x3 is 4 is equal to 1. That gives me x2 equals minus 3. Okay. I get x3 from here, I get x2 from there. If I want to do this one, I'm going to get x1 plus 2 times minus 3. And then plus 2 times 4 is equal to 4. And that's going to give me x1 equals 4. Let's see, this is minus 6. Take it to the other side, that's plus 6. Here we have 8. Take it to the other side, it's minus 8. So that's 2. So that gives x1 equal 2. And you can check that in the original system and find out that, yes, in fact, it is a solution. Okay, so that does it with this section.